So this picture, this 3D picture of these balls with springs attached to them, this would be a crystal lattice, okay, just like it says here. That's basically the way all metals, all conductors have this kind of structure to them. Now there are variations in, whether there's a ball in the middle of the side, or if there's a ball in the very middle of the cube itself. There's a number of variations on that, but fundamentally all particles, all materials, metals at least, have this kind of structure. And if you've had chemistry, you've seen the ball and the stick models, and when you put all of those molecules together, atoms and whatnot, you get a really well-ordered structure. And so these balls would sort of be representative of the atomic cores, and there would be electrons that are bound to them, and then there are electrons that are not bound to them. So these outer electrons, okay, they help with the bonding. But then there's this other thing, free electrons. And we want to talk about this thing called a mobile sea of electrons. So there's most of the atomic structure is fixed, and in sense of that, it's everything's vibrating. Nothing is completely motionless in this universe, as far as we know. We've gotten down to within a trillionth, I think, of a degree to absolute zero, and there's still motion. Right? So theoretically, there would be no motion at absolute zero because there would be no energy there. Whether we'll ever see that or obtain it is doubtful, in my opinion, but who knows what will happen. But anyways, there's all these free electrons. So basically, there's electrons that can move in between all of this stuff. And that's what current flow ends up being, is when the free electrons move through the lattice or through the conductor. So this would be just an infinitesimally small chunk of metal, a microscopic, nano-sized chunk of things. So just a way to visualize the internal structure. Now, essentially nothing but possibly a superconductor would be this perfect. It'd be sort of a twisted lattice, but you would recognize it as being this thing kind of twisted out of shape a little bit, but fundamentally that well ordered. All right? So that's just a picture of what's going on down on the atomic level. Let's flatten that out. So this gray-blue area is going to be the mobile electron. Well, let me use my colors here. So this gray-blue area is the mobile sea of electrons, and then the positive nuclei of each atom. So the plus signs are the positive cores. They're fixed. They're not moving. That gray stuff is what can move around them. So one way to maybe picture this is if we had a lake or a pool that had a bunch of red metal I-beams just stuck in the ground, and then a bunch of water, and that water could move. There was a wave pool or something to cause that water to move, wind, you name it, something sloshing around. Well, then you'd have all that water moving around these fixed points in the metal. So this would be that previous picture smushed down to a two-dimensional thing, and you're looking at positive cores that don't move and all this electron sea that can move. It won't necessarily move, but it can move. And in fact, perhaps another way to think of it is, bunch of people sitting in inner tubes, and then somebody opens the floodgate, and it all starts moving. All right, that sort of thing, or a wave pool, those sorts of things. So then this graph, let's look at this graph down here. And in a metal, you're going to have, some particle obtain a speed, and then it'll collide with something. And if we want to, and we do, we would want to imagine that that would be a collision where all that energy is transferred, and it goes back down to zero. Then something gets it moving, another collision. But all these collisions happen at different distances and therefore different speeds. So you have these different times between collisions and different speeds that these particles obtain between the collisions, but there'll be some average. And the average will be meaningful because there are so many of these collisions. As we've seen before, there are gazillions of these particles in just a little cubic millimeter of material. And so you would have just an insane number of particles colliding, free electrons colliding with fixed positive cores or other free electrons. Mostly, they will be bouncing off of each other as opposed to the positive cores. Be careful there, misspeak. But on average, there will be an average speed for the collisions that will represent the whole quite nicely. So here's a little bit more detail, so that the picture with the big red cores and the little blue balls. So the little blue balls are electrons. Okay, so this electron comes in here, misses the first two positive cores, bounces off. All right, this other one comes in here, zigzags around. So this is a snapshot in time. There's one that hasn't interacted with anything. Here's one that comes in, goes down, back, forward. So you can see all of these weird trajectories where, 2 steps forward, 3 steps back. All right, so what ends up happening here is that the drift speed, we'll find that the drift speed of this mobile electron seed is remarkably slow. You can outrun the sea itself. You couldn't outrun an individual electron, but you could outrun the mobile sea itself. Okay, extremely slow, but a lot of heat gets produced because there's a lot of collisions. So that's why bulbs get hot, and various things will get hot. If current runs through them long enough, they will heat up. All right. And the fellow who thought of this was a dude named Drude, Paul Drude. Came up with this model. So think about this in context of the movie. Faraday, pre-Civil War through Civil War era. Of course, he was over in Europe, missing all the fun. But that 1800s sort of game, early to late 1800s. I think he died in the late 1800s, if memory serves me well. So there was a lot known about current flow at this time, and he came up with this model, which has been a successful one. So this is just a way to picture it, think about what's happening on the inside, and understand the results that we observe. All right, so here's where we get into the math. So it's been a while since we've dealt strictly with momentum, but this has taken us back to first semester physics and the momentum principle. Delta P, P is our symbol for momentum, and delta P would be a change in momentum, and it's equal to net force times time. This is the impulse momentum theorem, where the amount of force and time, that product gives us what we call impulse. And so this would be like, you running into something, the time of that collision times the force of the collision gives you the magnitude of that interaction in terms of the momentum. So if I run into you as fast as I can, that will not be as preferred as a fly running into you as fast as it can, because I have a lot of mass comparatively, even though I could possibly go as fast as the fly. All right? So we start with this. You can apply the momentum principle to any motion in the classical world of objects. All right? So we have that. Now, on a single electron, net force is E net. So we take net force and it becomes this in the context of what we're paying attention to, which is a free electron. The force on an electron, a charged particle, will be the fundamental charge times the electric field. So we've defined previously that the electric field is the force per unit charge, which in this case is going to be force per unit E, which is why I can take my force and just write it little e, big E. That's taking us back to Coulomb. All right? So now we've taken this general idea of the momentum principle, and now we're getting it to be particular to what we're paying attention to. So the momentum formula becomes that. Now this right here. Assuming that the electron loses all of its momentum each collision. We do this because we can. Okay? Is it that always true? No. Is it sometimes true? Yes. But we always try to oversimplify things just so that we can do the analysis the simple way possible, and then if our experiment warrants some sort of other correction, then we take it from the simple up to the complex, as opposed to trying to start with complex and work it out. So if it loses its momentum, then you're going to have instead of a delta P, you're just going to have P for a mass velocity momentum thing. All right? So notice nothing really changed here. F net became EE net, and delta P became P, because we made an assumption about it going to zero, or losing its energy in that collision. So now we have a simpler formula, just since it's not a change anymore, it's just a momenta of this particle. All right? So we go from there, and now we let P is the same as mass times speed. That's the definition of momentum. And that since we're dealing with an electron, free electrons, they have a known mass, right? And momentum is mass times speed. So now we have the mass of the electron, the speed of the electron, and the fundamental charge of the electron, along with the field that's getting it moving. Okay? So we're drilling down slow into how this electron mobility, but we're able to, we know momentum involves speed, and so we want to, what's the speed of this electron? All right? So now, we seem to skipped a lot of work here, so realize that if I solve this for V, then I just get everything that's on the top here divided by the mass, which is all that we have here, but we make a little bit of, we take some liberty statistically. My speed up here from the momentum thing, instead of dealing with all of the particular speeds, I'm going to deal with one speed. I'm going to deal with the average speed of all the particulars. That's easier. Okay? And given how many we're dealing with, it's actually better. It's something that we can actually pay attention to, and it'll be close enough for that. But since I changed that one to an average, I also have to deal with the average collision time. Does that make sense? If I'm going to make the speed an average, I need to make the collision time an average, because that's what we were talking about. Going back to that zigzag graph diagram. All right? So we get away with that just because of logic. And it's necessary that we do that. And so now we have a formula, and I'm going to come out here just to bring things, but first let me zero in on this right here. So this right here is what that average speed can be described by in terms of the particulars of what's getting a free electron moving. And ultimately, the thing, quote unquote, that gets a free electron moving is the electric field that's applied to the region of space that that free electron's in. The charge itself, that's what little e, that's just a fundamental unit of charge, that doesn't make an electron move. The mass of the electron doesn't make the electron move, and the time of collision doesn't make the electron move. They're connected. All right, obviously it wouldn't respond to the thing that's moving it, the electric field, if it didn't have charge. The mass of the electron, it's a measure of its inertia, so it's going to resist that motion more or less than other things. Okay? And the time's just, every motion requires time. Going back to first semester. So what happens is we take all of this stuff and we create a constant. So the charge to mass ratio and the average collision time becomes this new thing called electron mobility. Those are the things that determine how mobile the electron is. Its charge, its mass, and the average time of collisions. But that only makes sense when there's an electric field applied, because they won't move. All right? So, like for instance, the lights in this room keep going off on the automatic timer, and it's a switch. It switches it off, and that switches off the electric field, and all of a sudden, the mobile sea of electron just stops moving. And since it stops moving through the light, and therefore it stops that interaction, and the light stops being emitted because the interaction has gone to nothing. And then we wave our hands, and it switches back on, and instantly the lights are back on. In spite of how slow they're moving, and we'll calculate that soon here. Because now we're able to. We have in this thing right here, the charge to mass ratio, those are fixed numbers. That's a number. We could look it up or just compute it. The average time of collisions is not something that's well known. And then the electric field, we can derive that from, say, the voltage that's applied and whatnot. Right? So that would be a variable that we control. So that's gets us to this thing called drift speed. And the reason why it's a drift speed is because we forced that average. All right? And so the drift speed is of the entire mobile sea. You'll read drift speed of an electron. It's really the drift speed of the sea of mobile electrons. We're pretending that they are all marching at the same speed, sort of in step there. That's false. That's not reality, but it's a good enough picture of reality. In reality, they're zigzagging all over the place, heating up everything, bouncing off, backwards, forwards, etc., which is why the whole group is moving so slowly. But it's just as efficient to just pretend that the whole thing's moving that way. Now, when we get into superconducting, which we'll just mention briefly in the thing, but in a superconductor, you do get that lockstep motion like an army marching. Okay? But it's still a slow, it's a bit faster because there's less collisions, less heat, etc., etc. All right. So, now here's this thing right here. Each conductor has an electron mobility that's unique to itself, and I'm going to blame it on the average time of collision. Because guess what? That's the only thing that's going to be different if you go back to that lattice structure that we looked at. Copper will have a different crystal structure than steel, than aluminum, than gold, silver. You just go through all the metals in that column, those columns of the periodic table. They all have a different crystalline structure. Therefore, the time between collisions will be different. If you had one electric field that's applied to these electrons that have a particular charge and a particular mass, the distance between collisions has changed, the environment has changed, and therefore, basically, each material will have a different time of collision, because that's the only thing that's changing if you keep the electric field constant, is the time of collision will be different because the metal structure is different. Right? So what we can do is we can work our way backwards to what that is based on, if we pick one field on an aluminum wire, copper wire, steel wire, etc., now we can know, the time between collisions on average is this. We also know about the atomic structure, and we know how far apart things are, the shells, etc., and so we can work our way backwards from this and kind of, if it matches with the reality that we've verified in other areas such as chemistry and whatnot, then we're like, okay. And the whole picture of reality is getting a little bit tighter here, and we cheated with an average. Because that's what we can measure. It's hard to measure the individual parts of this. So does that make sense, why that delta T, the average one, that gives us the uniqueness of each particular conductor? So it'd be like, running around in this room with the chairs put away, but then if we pull all the chairs out in the middle, running around in here changes. You're not going to run around it as fast. That would be like copper versus steel or whatever. The delta T would change. Therefore, the speed would change. All right, so here's kind of a summary. I didn't put that in the handout, now that I forgot about the table. But let's just kind of go through the motions here. So mobile charges. In a conductor, yes. Well, duh. That's why they're conductors. Because they have charges that can move. But in an insulator, no. They don't have charges that can move. Now, an insulator can obtain charge, but the charges can't move. So you can transfer charge to various patches on the outside of a insulator, but you can't get the charge to move through the insulator. You can transfer it to and from it, but you don't move it through it. Okay? We've talked about polarization a long time ago, at the beginning of the course, and in a conductor, the whole sea of mobile electrons move. Because we're already talked about that in our pictures in this lecture. Whereas in an insulator, it polarizes the insulator in there. So, but we're not going to deal with insulators. We're going to deal with conductors from here on out. The only insulators we're going to deal with are what's inside of capacitors. And they polarize, as we've shown in other things. Electric field is 0 on the inside of a conductor. It's going to take us a while to prove that. Okay? Current flows on the outside of the wire, actually. It's a surface layer effect. It's not on the inside. I even say that. Spread over the surface. Right? So mainly, this region of the table is what is the main event for this. So, all right.